Hello and welcome. This is the Exploit Development 105 lecture. My name is Dr. Owen Redwood, and this lecture is part of the Offensive Computer Security 2.0 OpenCourseWare, hosted by HackAllTheThings.com. Today's lecture covers return-oriented programming. In this lecture, we build up the basics of ROP, explain the fundamentals of return chaining, and gadget hunting. In the next lecture, we will discuss advanced gadget hunting techniques and tips, and we'll cover several types of gadgets that bypass most mitigations. Finally, in the next lecture, we'll also cover live demonstrations, so stay tuned for that. This lecture is solely on the fundamentals.
This is primarily a technique used to defeat DEP or NX and also code signing defenses. It is very related to return to library exploitation and also, in a sense, SEH exploitation with the pop-pop-red focus it has there. This is a pretty nice timeline of the history of exploit development. And as you see here, return-oriented techniques are really the latest state of the art. However, this timeline only goes up to 2010, so it doesn't cover return-oriented program defenses such as control flow integrity that are really become popular, and I don't see any mention of address-based layout randomization on this diagram as well. But in 72, that's when buffer overflows were first conceived. However, they weren't really used. Another way to put it is they were rediscovered about 20 years later. And that seems to be a common phenomenon in security, that someone thinks of something way ahead of the time. Even though buffer overflows, we think of them now, it's just like, that's so trivial. How did no one see that immediately? If you write to more than the allocated memory, sure, things are going to go wrong. We could maybe hijack EIP by overwriting the return address. And so buffer overflows are an example. Return to lib style, I believe, exploitation, first introduced by Solar Designer, and then later kind of publicly discovered by the masses. I guess they weren't all paying attention to them at the time. But then also return-oriented programming was, in my slides and my research that I have for this lecture, first thought of by someone in 2004, and wasn't until a 2007 paper was it kind of formalized and reintroduced to the masses, or as this diagram might say, rediscovered. So we're going to first go into return to libc and return to library style attacks before we jump into ROP for this lecture, because it leads well into that topic. And I haven't covered it just yet. So take this stack diagram. The stack obviously is going to grow towards lower memory, so it's growing up towards the top of the slide. And usually nowadays the stack is going to be memory protected. It's going to be set to not executable, so you can't really use shellcode. You can't inject malicious code, but you can still do buffer overflows and still control EIP. Maybe there's a stack cookie, but you can still brute force it eventually and still control EIP. So at that point, what can an attacker do? Well, imagine you've hijacked EIP and then return gets called, and you're pointing it to a function. Now think about what we know with how functions are called, and how things are pushed on the stack. First, the arguments to that function are pushed on the stack. And then finally, when the call to the function is made, it pushes the current value of EIP onto the stack so that it can return to that address. So the second we have the return address here overwritten, in order to call a function, we're going to have to do that same process. So the stack from this point down is going to have to look the same, but starting here. So once the return address is called, once return is called, it's going to pop this into EIP, and here where argument 1 is going to be the top of the stack. Now, as I said, what happens is you push your arguments, and then when the function is called, you push the value of EIP onto the stack, and that's going to be the top of the stack. And so this is going to be the top of the stack. So that's where we want our function, once it's done executing, to return to, if we want it to return cleanly. And then after that, this is where the first argument will go, and then after that will be the second argument, and so on. So a common way of spawning a simple privilege escalation shell would be calling system in libc, passing it the string binsh or a pointer to that string, and then telling it to exit afterwards. And so we're going to do that with a little example. So the basics of this exploit is you fill up the stack with just garbage all the way up to the return address. Overwrite the return address with the address of system. Then you follow that with the address you want system to return to. Then you append argument 1, which is going to be the address of the string binsh. Now, as you see, there's no writing code here. There's no writing shell code. There's no writing assembly code. There's no writing code whatsoever with this style of technique. So what we're going to have is we're going to take this innocent stack and subvert it such that when we overwrite the return address, it's going to contain the address of system. And then next is the address of whatever we want it to return to, or whatever we want it to execute next, and then argument 1, and so on and so on. So what we have to do for our given process is figure out the address of system, figure out the address of exit, and then figure out the address of the string binsh somewhere in memory. Now, I've already gone over this, and let's jump into a demo. So we're going to do a really simple privilege escalation attack with return to libc exploit. And what I'm going to do is exploit this little C program that comes with the book. It's pretty straightforward. It just does a stir copy and it's done. It's nothing to it. So to illustrate what we're going to do, let's pull up this diagram. We're going to have to find the address of system. So let's pull up the program in GDB, set breakpoint on the main function, tell it to go there. Now the process is initialized, so we can find the addresses of various functions. So print system, print exit. That's going to tell me the address of system and the address of exit. And now what I need to do is find the address of some binsh string in the process space. So if you're familiar with Linux and Unix, you may know that there's often an environment variable called shell that specifies the preferred shell for for a given user that's logged in. Now I could use this one, and I'm going to demonstrate why there's a little problem with it right after I get it all to work, because there's a nuance that requires there's a space in a certain place in order for it to all work. But what I'm going to do is, in the absence of such an environment variable, let's just create our own. Oops, export binsh. And these spaces at the beginning are what I'm talking about. So I'm going to use this function, this program that comes with the book's source. It's pretty simple. I'm not going to cat it out, I've already shown it. But get environment address of binsh in the program full. It's going to tell me that binsh is going to be at this address. So now that we have the addresses of everything, we have to find out where this return address is going to be on the stack, and how we're going to find it. So what we're going to do is throw a very large pattern at vuln, and I have it generated from Metasploit, and as you see, it's going to cause a stack fault. So let's run vuln in GDB and tell it to run with the parameter we've just given it. And you see this indicates where the return address has been overwritten. And as we backtrace, this is where the I guess beginning of all the problems are for the program. So what we're going to do is translate this into ASCII because it's stored in hex right now. And so 6.1, according to our handy ASCII chart, which you get by just typing man ASCII, is going to be lowercase a, so it's going to be a in the mix. Then 3.9 is going to be, scroll down, a 9. This is a 9. And then 4.1, well, if you didn't already know, 4.1 is capital A, which is to show you. Here we go. A, and then 6.2 is going to be lowercase b. 6.2, b, b. So this seems to suggest that it's getting somewhere in the middle of our sequence. So let's figure out exactly where it is. I use Python for this, and I just set a string equal to my pattern, and then for my substring, you can confirm that it's in the pattern by typing A9, A, B, and X. Well, it's true. So now we do x.find in our string. It's going to tell us it's at location 28. So if we do the C, start printing out X at that location, we see that yes, indeed, that is the case. So we have to generate about 28 characters in order to start overriding the return address. And so what we're going to do is quit out of GDB over here. Yes, 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 yes. All right. So let's go back. Actually, GDB, break on main, print out system. Tell it to go to main. Print system, print exit. And then we'll get the environment address for our special binsh string. What we're going to do is the exploit, oops, is going to look like 28 characters plus first the address for system, which is going to be right here. And we have to encode this in little endian. So 80, ED, B7, then the address for exit, so F0, 68, EC, B7, then the address for the string, which is going to be 65, FE, FF, BF. And I think I've made a tiny mistake. So I believe the mistake is that this is just off by 1. And there we go. So we've spawned a new shell, we play around, and the privilege escalation attack in theory works. And that is it for the demo, showing how you can pull off a exploit without actually writing any shellcode, just by forcing malicious computation. So that was a toy example, but over the years,
it has grown easier to find vulnerabilities,
but it's growing harder to reliably exploit them because of exploit mitigation such as DEP, NX, ASLR, things like EMET and control flow integrity research is being done now, and whatever the future may bear. So return to libc is kind of a subset of the overall art of return-oriented programming. It was conceived in 2004 by Sebastian Kramer, and there's a paper here. However, it was kind of formally introduced to the world in an academic paper titled The Geometry of Innocent Flesh on the Bone, Return into libc without function calls on x86. So the author, Hovav Shacham, demonstrated the concept of using gadgets, small little snippets of assembly code, of opcodes in the binary itself, and chaining them together to do a few instructions and then return, and then chaining a series of these together to perform an overall greater function. What Hovam Shacham did, I believe in his paper, was demonstrate with exploit code that he could do a search for all the gadgets in a program and put them into a catalog. And this catalog would then be tied into a higher order compiler, and you could write exploit code for the compiler, and the compiler would try to achieve the functionality that it was specified to produce with the various gadgets strewn throughout the program. And he showed that this ROP gadget compiler is actually Turing complete, which is very interesting. And to prove it, he demonstrated a quick sort exploit, and the program would take in two strings. One of them obviously was a buffer overflow, and he exploited that, and that's where his ROP code went. And the other was actually a string full of numbers, and his ROP chain simply performed a quick sort on the other string. Not doing any malicious code, just demonstrating what we call a weird machine, if you will. It was a kind of landmark publication in the field of exploit development as well as security, showing there are no theoretical limits to code reuse attacks, in that you can basically form a Turing complete compiler with all the gadgets in an application, provided that there are enough gadgets. So overall, return-oriented programming expands the bag of tools you have in this arena by introducing gadgets that can perform control branches, loops, conditional branches, and the standard return into library techniques that have been used up to that point didn't support, or you didn't find in the wild, any use of conditional branching. And this made it so that if there were some weird memory protections or weird security mechanisms at the time that prevented the specific use of return into library technique, you could recreate the functionality of that target library that you wanted with other gadgets strewn throughout the application. So, say for instance, the defense was the developer stripped out the system function from libc, and that would have broken this demo we just showed. However, with the overall approach of ROP, all you have to do is recreate that functionality by chaining together the right gadgets that are already in the application. So it is completely dependent on the calling convention. And this is why we introduced the calling convention early on. We covered cdecl, we covered standard call. We did not cover fast call. Fast call is an important calling convention used in Linux where the first 6 registers are used to store variables as opposed to the stack. Then after the first 6 registers are occupied, if the function takes that many arguments, it begins using the stack, or at least a pointer to an array of the remaining arguments, which is likely going to still be stored on the stack. So cdecl is what we're going to be using for the rest of this lecture to finish illustrating how ROP works and return chaining works. cdecl originates from C. The arguments are pushed on the stack in right to left order, and then the calling function cleans up the stack. And that means that when I push the arguments on the stack and call the function, when the function returns, I have to remove those arguments from the stack. So standard call originates from Microsoft and actually makes ROP way easier because I don't have to worry about the cleanup. If I were ever to call a function, it cleans up the stack for me. And like cdecl, standard call, the arguments are pushed in reverse order and from right to left. Fast call, actually let's go to Wikipedia about fast call, because there are a number of different implementations. So when I say fast call, there's not one right answer I'm identifying, or implementation I'm identifying. So according to Wikipedia, conventions that are called fast call have not been standardized, and there are different implementations, and it depends on the developers of whatever compiler is using this. So the thing that's important to remember is that across all the implementations is that the fast call calling convention typically uses one or more arguments being located in the registers. And Linux fast call uses the first 6 registers. And that's the one in the homeworks that we'll refer to. So as you see, there's Microsoft fast call, there's Borland fast call, there's something called Wacom fast call, and there are a number of other calling conventions. And so how a calling convention works completely dictates how ROP techniques will work against that architecture. So we're going to focus on cdecl for the rest of this lecture because you guys need to understand how to be able to clean up the stack between each ROP gadget call, and between each function call if you're chaining together functions. And we're going to be diving into something called return chaining. So if you recall with our very simple example, I apologize for the diagram being inverted. The stack is growing to the bottom of the slide. This is lower memory and the top is higher memory here. If you remember, we chained the return from system to go straight to exit. What if we wanted to go to an arbitrary function, maybe jump from function 1 to function 2 to function 3? Well, we're going to have to be able to set up the arguments for each one. And if we don't clean up the stack and say exit here is the next function, well, it's going to think that argument 1 is going to be its return address, and then after that, arguments for it are going to start here. So it's going to take argument 2 as its first argument. And obviously that's going to mess things up. It's going to be very unlikely that we're going to be able to pass something to one function and be able to just cannibalize the arguments. So what we do here in ROP is, in order to clean up the stack, we're going to pass the return address for a given function to a gadget that's going to clean up things for us. It's going to call a number of pops to pop the values off the stack and then to return to a function pointer that we want it to execute next. So the number of pops that are going to be in your gadget are going to match the number of arguments that you've pushed for this given function. So we execute function 1. It does its thing. It uses argument 1. It uses argument 2. And then when it returns, ESP is going to be here, and return is going to do pop ESP. It's going to take this, jump to this gadget, and this gadget is going to have 3 instructions. It's going to have like pop EAX, pop EBX, return. Now, it doesn't really matter most times what register you're popping something into. However, if you're chaining things together in such a manner that you want to set specific registers to things, this may be used in such a way to populate those registers. But let's get to that in a little bit. You may be better if you worried about certain registers. Say you're using EAX, EBX, and ECX to do some sort of system call later down the line, and you don't want to, have your cleanup gadget trash those registers. What you're probably going to have to do is find some pop instructions that pop things into like EDI, EDX, ESI, as long as those registers aren't being used in whatever you're jumping to. On the other hand, let's say function 1 actually took no arguments, but we want to set up registers for function 2 to do its thing. And we're jumping into the middle of function 2 and avoiding some maybe potential security checks. But before those security checks, it sets up 2 registers. The way we can use the same technique to get around that is, say, argument 1 here is instead I want it to be EAX. And argument 2 here is what I want to be EBX. And those get set up, in the first half of function 2 that we're skipping. By doing this sort of gadget, if I do pop EAX, it's going to set EAX to what I want. And if I do pop EBX gadget here, it's going to set argument EBX to be what I want. Now, all of this has restrictions on null bytes. Obviously, if you're doing this in a buffer overflow, it can get really tricky. And then obviously it will call return and jump to the next gadget and so on. And so this is how return chaining works. There are probably a number of other techniques that are just twists on each thing I've said here. And this can all be used in different combinations of techniques to chain together individual gadgets, little more complex gadgets, all the way to reusing entire functions. Now, there are some functions that are completely reused to defeat security mechanisms like dep and NX. But let's not get ahead of ourselves. Let's walk through all of this with a very simple example. Say we've exploited a vulnerable function and it's finally getting to ret. And this is basically going to pop the top of the stack off into EIP. And there it goes, and heads, the processor points at whatever function we've indicated it to go to, and it's going to do its thing. It's going to have its little prologue and its epilogue, and stepping through each line, it's going to push EBP, it's going to use the arguments, it's going to then clean up, restore the stack frame, and then it's going to call return. And this is going to, for instance, if we have pop EDI, pop EBP, EDI is going to take argument 1, EBP is going to take argument 2, and then it's going to return. And that's going to go to function 2, and so on, and so on. So the overall theory behind return-oriented programming is basically a combination of return to library style techniques and a combination of return chaining. It has been used in malware going back to 2008, 2006, I believe, to disable data execution prevention in Windows systems. It's also, you can use it to disable NX in Linux systems. And effectively, what they're doing is reusing the same code that's in the process space that is used to set up the whole process when it's initialized. And first, the operating system maps out the memory segments, and then it jumps to the .text, and the .text then establishes the security mitigations and permissions for each memory segment. And so the code to actually enact dep is in the process itself. And so what the attackers do is they reuse the same functions to disable dep on the stack. Dep was not permanent in the beginning. And so Windows in Service Pack 3 for XP, Vista, and then Windows 7 by default respond to this style of attack with permanent dep. However, this defense was off by default and applications had to opt into permanent dep, which was just absurd. I'm not sure if that's been fixed nowadays. However, the main technique that's being used with ROP to get around dep and NX is stack pivoting. And we'll get into that in just a little bit. So defenses have been evolving to mitigate the early ROP attacks and the ROP attacks going on now. And attackers have evolved their techniques in this arena also. So instead of returning to functions and existing instructions, you can actually return to inside the middle of an instruction. If an instruction is more than 1 byte for an opcode, for instance, most move instructions or most instructions dealing with actual data that's hard-coded are many bytes long. So, as an example, completely stolen from Dino Daizovi, I'll admit, if you take the instruction move EAX C3084189 and anything ending in 89, because it gets a little ending encoded here, if you just jump to past the first byte to the second byte, actually, it's going to be decoded as move into ECX plus 8 EAX and then ret, which is really fascinating. So just because you get rid of perhaps dangerous instructions themselves, there's nothing preventing an attacker from jumping into the middle of existing instructions, or perhaps the middle of an existing instruction that decodes into the next instruction when it's interpreted like that. For instance, if the middle here was B8, that would be move EAX and then some integer 4-byte combination. So if 41 here was B8, it would go on for the next 4 bytes into the next instruction, decoding instructions as a single move and putting all that value into EAX. So attackers really only just need usable byte sequences that represent valid instructions. And they have to be obviously in executable segments for them to reuse them. But that throws a huge wrench into defender attempts to carve out undesirable gadgets. So this was a serious level up for code reuse attacks, and this too is a gadget jumping into the middle of an instruction. At their most atomic and simplest level, ROP gadgets are just single instructions followed by a return instruction. And chaining these together can allow you to set registers, to move things between registers, and etc. And this can lead all up to calling an overall function, as well as we demonstrated to provide stack cleanup for return chaining. So it is common to actually build a catalog of route gadgets for a target application to just scan executable memory for all sequences of a useful instruction followed by a return instruction. And then by forming a catalog of these instructions, you can have a compiler on the front end of the catalog that takes a higher level language and compiles it down into ROP gadgets that functionally is equivalent to what is specified by the higher order language. And when you use this in an exploit and it all manages to execute, you land the exploit, blah, 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 it will perform what you have specified in the higher order language. And given a sufficient amount of gadgets, in other words, given a sufficiently large application, most gadget catalogs and compilers will be Turing complete. So in computer science theory, for those of you who don't come from a CS background, a system of data manipulation rules or a processor or an algorithm is said to be Turing complete if it can be used to simulate any single tape Turing machine. I understand that for most people outside of CS, this is like using the word itself to define itself and doesn't mean much. I don't want to delve into the theory behind Turing completeness and get into a lecture on Turing machines and why this is all important. However, sufficient criteria to demonstrate Turing completeness involves typically conditional branching and the ability to modify arbitrary memory locations. These two criteria are sufficient, but aren't always necessary to demonstrate Turing completeness. Whoops. So ROP gadgets can still be difficult to work with. You're passing in a series of addresses, and for 64-bit targets, it's very likely that the upper parts of your address are going to have a lot of null bytes, and you won't be able to use many gadgets. So just like ASCII shellcode, if you're doing this in a buffer overflow, it's going to be a problem. So looking at things from the terms of a ROP gadget compiler, a ROP catalog can be seen as the instruction set used by your victim process. In other words, you're turning the victim process into a weird machine, and your ROP gadget catalog is that weird machine's instruction set. That's perhaps the best way to put it for fellow hackers. So there are plenty of articles on ROP gadget compilers and how to build your own. However, probably the best one I have is a blog post and a series of blog posts for required reading this time and next time to go over that. So we have Hovland Shasham's initial paper, the return-oriented quicksort technique, and that awesomeness, and there are others. And in the end, the main thing attackers want to defeat is dep. And with permanent dep, you can't call the same function that's used to set up dep to disable it. What you're going to have to do is something called stack pivoting. And that's where our guest lecture next time is going to pick up. But at its core, stack pivoting effectively relies around allocating new memory space, a new memory segment, specifying that memory segment to be both writable and executable, moving your payload there, pivoting there, and then executing as normally. So many exploits are multi-stage. Defeat dep with ROP, either through disabling dep or doing a stack pivot and then execute a traditional payload. Now, I hope you all understand this so far, because now you have to think about how address space layout randomization affects ROP. Full ASLR effectively mitigates ROP, because you're relying on knowing the addresses for all these gadgets and for them to be at a fixed location across all targets. Now, with ASLR, every time that process is executed, those memory segments are loaded in a different location. So that breaks any exploits that rely on fixed addresses of targets or gadgets. The way to get around ASLR with ROP is either brute forcing or a memory leak or info leak. The two terms mem leak or info leak are kind of synonymous, or they're used as synonyms in the hacker culture. And effectively, what they do is if you can leak the the address of a variable that you perhaps know is static within a memory segment, you can have an anchor within that memory segment that you know the address of, and then you can address everything relative to that. That allows you to defeat ASLR, but it's on a per memory segment basis. So that's where things can get tricky. So DEP, as I said, does nothing to prevent the allocation of more memory. It's simply the DEP functions are used to, after the process has been initialized by the operating system, to once it's starting up, enact all the memory segment permission protections. So the thing is, since 2003 and going into this year, DEP and ASLR in conjunction are actually very common. Another term that's synonymous with memleak or infoleak is address disclosure. It all means the same thing, and it basically is used to give the hacker an idea of where things are, and that can be used to relatively address things and perform a ROP, which is then used to defeat DEP, which is then used to execute a more traditional payload. Typically, entire traditional payloads are not written in ROP, though there have been some few exceptions in the wild that people found with PDF exploits. There are tons of databases of ROP gadget chains out there nowadays that work on most platforms, and they're specifically for common DLLs and common shared objects that are used. For instance, maybe crypto libraries are very common, encoding, encryption, compression libraries, etc. GUI libraries. This is an example of a ROP chain. It is effectively a ton of addresses strewn together, and I believe this is for standard call, but I don't know. I didn't write this. But from a forensic standpoint, this is going to look different than shellcode. Obviously, shellcode isn't going to be instructions that are fixed width that look like addresses every single time. And you may find some values that are hard-coded in here that are getting moved into registers, and that may throw you off if you are looking for patterns to identify a ROP chain. So you have to be aware of the calling convention of the architecture that you are protecting, whether it's Linux or Windows, and how that will affect doing forensics against ROP chain exploits. So, like I said, calling conventions are important. And the key lesson is that preventing the introduction of malicious code is absolutely not enough for preventing the execution of malicious computations. And who knows what the future will bring in this arena. I assume things will always still be exploitable. So these are some good introductory articles, starting with the gentle introduction on ROP, and Dino Daizovi's practical return-oriented programming presentation is also very good. Corland's tutorials on ROP are excellent, and for the required reading, we're going to focus on the ROP-C compiler, which allows you to write source code that gets compiled to a ROP gadget catalog. And next time, Devin's going to be the guest lecturer, so I expect you to all be in class, and he's going to start off with stack pivoting, and we're going to go through some ROP examples, go do some demos, use a catalog, find gadgets, and